everyone. In this video, we are going to be giving you an introduction to MPI and how you can test the performance of your MPI application with the Survey HPC performance tool. Survey is an HPC performance tool from all of us at Trenza Synergy. When you measure a run with Survey, you can opt to use the extended MPI metrics. This is what those extended MPI metrics look like in a run of XHPCG. This video is going to explain what those metrics are and how you can use Survey to determine the performance of your MPI HPC application. MPI stands for Message Passing Interface. It is a standardized communication protocol for passing messages within a parallel computing application. Basically, it's a way to divide a big computational problem into a bunch of smaller computational problems and give them to different computational threads. Each thread solves its piece of the problem and exchanges messages with the other threads when needed. There are several different implementations of MPI, including, but not limited to, OpenMPI, MPitch, and MVAPitch. Each implementation has a slightly different syntax, so when you see instructions for how to run a particular MPI application, you may need to adjust those instructions slightly depending upon the MPI implementation you are using. For best results, you should also make sure that you are using a version of Survey that was built with the particular variety of MPI that you are using with your application. There are two major categories of MPI messages, collective and point-to-point. Collective operations, as the name suggests, are operations that require the participation of all ranks within a communicator. This is often, but not always, all ranks within the application. Some examples of collective operators include MPI reduce, which has operations such as sum and max and min across all ranks. For example, if each rank solved a piece of the problem and you had to add all the pieces from each rank together to get the solution, you could use MPI reduce with the operator of sum. The way this works is that every other rank would send its solution to a neighboring rank, and that neighboring rank would take that sum plus its own sum together. And then every other one of those ranks would send the new sum to its new neighbor, which would then add those sums together. And this goes on until there is only one data point left and all the data has been added together. What happens to this operator when you add more ranks? This increases the number of steps needed to solve the problem. In our simple example of 32 ranks, there are log base 2 32 steps, which is 5 steps. If you had 64 ranks instead of 32 ranks, there would be 6 steps. This might not seem like much, but if it took X seconds to pass a message, then the operation would go from taking 5 times X to taking 6 times X time, which is an increase of 20%. Of course, this is a vast simplification that assumes the message size is the same, even when the number of ranks is increased, and that's not necessarily the case. But the point is that when you increase the number of ranks to MPI applications, you are adding significant additional overhead every time you pass one of these types of messages. Other collective operations have different patterns with a different amount of messages per step, but they all involve a logarithmic number of steps. The other major category of MPI operators is point-to-point. And that is when two different ranks communicate directly with each other, usually with MPI send and MPI receive. This communication pattern takes 1 or 2 steps to complete, and unlike collective operations, the number of steps doesn't increase when you add additional ranks. Sometimes adding more ranks will decrease the problem size of any particular rank, which may make the message size smaller, decreasing the latency for these types of messages. But that is entirely dependent upon the application. MPI provides both blocking and non-blocking calls. In a standard blocking MPI send message, the call doesn't return until the message has been copied out of the message buffer and into the communication system, making the buffer available again. In a non-blocking send message, the calls return immediately, allowing the thread to perform other useful work. In order to determine that the message has been copied out of the buffer, allowing another message to be sent, requires a call to MPI wait. So often the extra time that the blocking MPI send takes waiting for the buffer to clear can be consumed by calls to MPI wait. Blocking and non-blocking MPI receive calls are similar. In the blocking MPI receive, the call will not return until the data has been copied into the message buffer. With the non-blocking MPI I receive, the call will return immediately, allowing the thread to do more work, but a call to MPI wait will be needed to be performed in order to ensure the data is safely in the buffer. When the extended MPI measurements are included, Survey can tell you what kinds of messages your application is using, how many of these messages were sent, and the approximate sizes of these messages. To run Survey with the extended MPI measurements, use the command survey --use MPI extended, that's EXT for extended, --block report, and then your application call. For example, survey --use MPI extended, --block report, srun n64./xhpcg 200 200 200. Here's an example of the Survey extended MPI measurements of xhpcg performed with 64 ranks. The total test time was 7 minutes and 49 seconds. The first MPI calls shown are the ones to MPI init and MPI finalize. Not surprisingly, there was one call to each of these functions starting and ending the MPI functionality. The Survey runtime collector measures the performance of all ranks of the run. Then the Survey analysis engine takes over and collects statistical information about the run, including the min, max, and average across all ranks of each measurement. In this extended MPI report, the values shown here for the time it took for MPI init is actually the average time it took for MPI init across all 64 ranks of the run. The maximum, minimum, and other statistical information can be found in the JSON report file. If you are really interested in digging into the weeds, the per rank raw data is available in the tar file created by the run. So this shows us that the average time for MPI init to complete across the 64 ranks was 13.327 seconds. The average time for MPI finalize was 0.989 seconds. The next measurements shown are measurements of the point-to-point functions. In this case, xhpcg uses a combination of the blocking MPI send function and the non-blocking MPI I receive function. When some combination of MPI send and receive, whether blocking or not, have the same number of calls using the same number of bytes, Survey reports these values together for better readability. In this case, each rank has 25,711 calls to MPI send and 25,711 calls to MPI I receive. Of course, the time these calls take is going to be different for the send call than it is for the receive call, so these times are reported separately. Remember, the time shown here is the cumulative time for all 25,000 odd calls averaged across 64 ranks. Next, we can see the histogram for the MPI send and the MPI I receive calls. This histogram breaks out the calls into size bins. The first bin shows all the calls with a message size ranging from 0 to 16 bytes. The second bin shows all the calls with a message size ranging from 16 bytes to 64 bytes, and so on. This shows there were 5,933 calls to both MPI send and MPI I receive in the 16-byte bin, containing a total of 47,466 bytes each. The average total times for each function are also shown. No calls were made for message sizes between 16 and 64 bytes, but 1,060 calls were made with the message sizes between 64 bytes and 256 bytes, for a total of 211.94 kilobytes, and so on. This histogram gives you a very good picture of what kinds and how many messages were used by the application. Next, we can see the results of calls to MPI all reduce. There were 555 calls for an average total of 35.719 seconds, with 4,440 bytes total for each rank. In this case, all the messages to MPI all reduce were in the same bin of size 0 to 16 bytes. When there is only data in one bin, we don't display the entire histogram, just the results of the single bin. Finally, we have the results for MPI wait. MPI wait is used by MPI I receive to determine that the data being received has been copied into the receive buffer. Oftentimes, any data saved by using MPI iReceive instead of MPI receive can be found in this call. In our case, there were 25,711 calls to MPI wait. That's the same number of calls as MPI iReceive, for an average total time of 13.921 seconds. Notice there is no data noted for this call. Although MPI wait involves internal MPI system calls, they don't involve any actual application data, so we don't have any data to report here. And that concludes the extended MPI report. Of course, Survey also measures a lot more data than the extended MPI. Make sure to check out our other videos for more information on Survey's other measurements. If you like this video, please give us a thumbs up. If you are interested in other similar videos, hit the subscribe button. Once you are subscribed, if you want to be notified of future videos, click the notification button. Thanks so much for watching.